In today's video, I'm answering this Edexcel GCSE Physics Paper, Paper 1, and it's for the 9:1 specification, and we're going to be doing a complete walkthrough of this specimen paper. So, starting with question 1, there are many different types of waves. Waves on the surface of water are transverse waves. Sound waves are longitudinal waves. Describe the difference between transverse waves and longitudinal waves. This is a very nice question to get you going with. You simply need to state the definition of transverse waves and compare that to the definition of longitudinal waves. And don't forget, my perfect answer revision guide has all these definitions in there in the most concise way possible. So transverse waves have vibrations which occur, and this is the crucial word, perpendicular to the direction the wave is travelling in. Longitudinal waves and you're using the exact same definition, do notice this. But the crucial difference is that the vibrations occur parallel to the direction in which the wave is travelling. B. Figure 1 shows a ripple tank. This is used to study the behaviour of water waves. So let's have a look at what we've got. Well, we have a support which has a wooden bar hanging off it, and I think that's going to be what's creating the waves on the water. And then you have a light source which is shining down and it's creating shadows of those water waves onto the screen below, and we have a length given as being 80 centimetres. Water waves are produced in the tank. The shadow of the waves is projected onto the screen below the tank. The waves appear to move in the direction of the arrow. Describe how to determine the frequency of the waves. So really you need an equation here, and that is that frequency equals number of waves over time taken. So clearly we need to measure the time taken for waves to pass a particular point. And once you've measured both of those values, so the number of waves, the time taken, then you'll be able to calculate the frequency. And don't forget that frequency is measured in hertz. Units are so important. The screen is 80 centimetres long. What is the approximate wavelength of the waves as seen on the screen? So let's have a look at, we can see that this length here is 80 centimetres. And so the wavelength is really the distance between the two wave fronts here. So effectively you need to count how many waves you can see. And don't forget, the water waves are obviously occurring up here, but their waves are being projected onto the screen below, which is fine for us to use the screen here. So count the number of waves. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So effectively you need to do 80 divided by 19, and that gives you a value which is approximately 4. So if you have a look, you can see that option A is 4 centimetres, so that's why that is the correct answer. The student uses the image to estimate the speed of the water waves as 75 centimetres per second. Which of these is a reason why the estimate is not correct? And really, for me, the biggest problem here is we're using an image. If you have a look, the image being produced on the screen is much bigger. So the waves being produced on the screen is much bigger than the water waves themselves. So that's going to really impact our wave speed. And let's have a look and see if any of those answers mean that. The student used a ruler without millimetre markings. That would not be a reason for 75 centimetres per second being incorrect. The light was not bright enough. If you can see a wave, you can see the wave. The student's measurement was inaccurate. Potentially, if the fact that D wasn't an option, that the wave seen on the screen is magnified. I already said an answer along those lines. 2a. Scientists no longer accept the geocentric model of the universe, but it was the accepted theory for hundreds of years. Explain why the evidence available at the time supported the geocentric model. So what is the geocentric model? Well, that's the historical but incorrect model of the solar system, which is that Earth is at the centre. And as we know to be the case today, the Sun is at the centre of our solar system and all the planets and moons orbit the Sun. So, explain why the evidence available at the time supported the geocentric model. So why would people think that Earth is at the centre? Well, firstly because they had no scientific evidence. The only evidence they had is what they could see with their eyes. And what was this evidence they could see with their eyes? Well, it showed to them that the sun and the moons appeared to move across the sky in the same direction. And due to that, people thought that them sitting on the Earth meant that they were in the middle of the solar system and that the sun and the moons were just zipping past. B. The Big Bang theory and the steady state theory are two theories about the origin of the universe. The discovery of CMB led scientists to accept only one of these theories. Explain why redshift supports both of these theories, but that CMB supports only one of them. So we need to make some very basic comments, first of all, about what these two theories state and what they have in common. So you want to start by saying that both theories state that the universe is expanding. But that only the Big Bang theory states that there wasn't really a beginning where there was a huge explosion which sent all the matter whizzing out into space. And so if we now look at our pieces of evidence, let's first of all take redshift. Now, light from distant galaxies is redshifted, which means it has a longer wavelength, therefore indicating that these galaxies are moving further away from us. So actually, the redshift theory does indicate that the universe is expanding and therefore supports both the Big Bang theory and the steady state theory. However, the CMB which is present has to provide evidence for there being a beginning, and that's why it only supports the Big Bang theory and it is unable to support the steady state theory. Oh no, haven't been concise enough, falling off the edge of the page here. C part I. A star with a mass very much larger than the Sun. Okay, so what do we know about our various stars and, depending on their size, about their life cycles? So let's take a large star to begin with. So it goes through its main sequence, which is actually longer than that of a small star. And then it swells up to form a red supergiant, followed by a supernova, which is a huge explosion. and then either a black hole or a neutron star depending on its size. However, a smaller star such as our Sun enters a shorter main sequence, swells up to form a red giant but not a supergiant, and then a white dwarf followed by a black dwarf. I do love these names. So let's have a look in these options. So a star with a mass very much larger than the Sun has a longer main sequence than the Sun and ends as a white dwarf. No, there's no mention of a white dwarf in my largest star notes. B has a longer main sequence than the Sun and ends up as a black hole. Yes, that's definitely a potential. C has a shorter main sequence. No, I already know that's wrong. D has a shorter main sequence. No, that's wrong again, which is why the answer here has to be B. Which row has two correct statements about black holes? So a black hole is something which, it kind of really freaks me out because basically nothing can escape it. Nothing at all. No light, nothing. Nothing. And that's why we can say that no electromagnetic radiation can escape. And if you have a look at what I have written in terms of forming a black hole, you can see that it comes from a very large star going through its red supergiant phase followed by a huge explosion. So let's have a look and see if any of these options match up with that. One thing I do want to point out is a nebula is completely wrong because that's the very beginning of a star's life. So it wouldn't be a nebula collapsing. So that's why A is wrong. B allows nothing to escape. Yes, that's true. A very large star collapses. Yes, that's true. C allows nothing to escape. Yes, that's true. I've already said why it's not a nebula collapses, so C is incorrect. And then D only allows electromagnetic radiation to escape. No, I've said even light can't escape. So that's why B is the only right answer here. You do need to know a lot about stars though. 3. Figure 2 shows some lines in the absorption spectra from 4 different galaxies, A, B, C and D, and from a laboratory source. All the spectra are aligned and to the same scale. So we've got A, B, C and D. Explain using figure 2 which galaxy is furthest away from us. Do notice that we've got this wavelength here identified, and that's because it's the only thick line, and really that's our reference point. We're going to be comparing the thick line on A, B, C and D. And the other thing to notice is which galaxy is furthest away from us, and that means is the most redshifted. Because remember, when galaxies move away from us, their wavelength effectively gets stretched like this. The wavelength is longer, and then if you look at these wavelengths along the bottom of the scale, you're looking for the longest wavelength. So which one is the most redshifted? And the longest wavelength you'll find towards the right hand side. It's the furthest right of these lines, which is why, I hope you can see this, which is why this is the answer, C, because it has been the most redshifted, and we're going to write about that now. Galaxy C is furthest away. Because it has been redshifted the most. And is therefore travelling at the fastest speed. Cool, and that is done. Part 2. In figure 2, the reference wavelength is shown at 390 nanometers. Estimate the change in reference wavelength for the light from galaxy D. So going back up, right, we have our reference wavelength, which is here. This is going to be hard for you to see. I'm just going to change colour. And it's moved to here. So you just want to use this scale to help you identify it. And if you have a look, you'll see that that is approximately 20 nanometers. but they would have accepted any answer between 19 and 25. Calculate the speed v of galaxy D, use this equation. We've been given the speed of light, and just be really careful with your units because we've got nanometers up here, meters per second here. So actually, although they've given us the equation, we do need to just be a little bit careful. So I'm going to write the equation out. V equals c delta lambda over delta 0. C, we've been told, is 3 times 10 to the 8, so that's the speed of light. And according to this equation, we need to multiply it by delta lambda, which we've just worked out in the question above, is 20 nanometers. And then be careful, you need to convert nanometers to meters, and the way in which you do that is by doing times 10 to the minus 9. So we're going to pop that conversion in here, and then divide the whole lot by delta 0, which we know is 390 nanometers. So 390, and then we multiply that by 10 to the minus 9 again to avoid any issues with units, and we get a final answer which is huge. It's 15,400,000 meters per second. B. Figure 3 shows a photograph of galaxy D. The photograph is taken by a student at his home. State 2 ways that the student can improve the observation techniques so that the quality of the image is improved. Some of this will be common sense. So for me, that would be move your telescope to better viewing conditions. And that's actually why a lot of these satellites are found in deserts. There tends to be very little light pollution, very clear skies. So I'm just going to write, because I like this answer, move the telescope to better viewing conditions. E.g. in a dry desert. Something else you could say is use a better quality objective lens. Can you hear the ice cream man? It's not even warm. And if anyone's listened to my first chemistry video, you'll know there was a dog banging and a builder doing something else. London is so noisy. Something else you could have said is use a wider aperture camera or use longer exposure time while the telescope is locked onto a star. Figure 4 shows 2 students investigating their reaction times. Student B supports his left hand on a desk. Student A holds a ruler so that the bottom end of the ruler is between the finger and the thumb of student B. When student A releases the ruler, student B catches the ruler as quickly as he can. The investigation is repeated with the right-handed student B. You might have done this in biology actually, to do with the nervous system. They quite like this. Anyway, A, the students took 5 results for their left hand and 5 results for the right hand, and figure 5 shows their results. So we've been given the average for the left hand, and for the right we need to do that now. Calculate the average distance dropped for the right hand. Give your answer to correct 2 sig fig. Please guys, don't lose a single mark for not rounding properly or not even bothering to. That would be a terrible way to lose marks. So in order to do this, we're calculating the mean, the average. So we need to do every trial and then divide it by the number that we have. So we have 5. And when we've done that, we get an answer which is 18.36. And if we round that to 2 sig fig, it becomes 18. Calculate the average time for the left hand and use the equation time squared equals distance over 500. So we've got the distance as being 14, so make sure we're using the right answer here. So time squared equals 14 over 500 to get time squared equals 0.028. Then we need time by itself, which means we need to square root both sides effectively. You get a value which is 0.16733. Let's round to 2 sig fig, seeing as you guys tend to be asked to do that a lot, so that's going to be 0.17 seconds. Explain whether any of the readings are anomalous. So anomalous really means odd one out. So let's have a look up and see if any of these don't fit the trend. And hopefully you can see this 25.5 is much higher than all the other readings. So I'm going to write that here. 25.5 is an anomalous result. I can't spell anomalous, oh my goodness. There we go. Because it is much higher when compared with the other results. Give 2 ways that the students can improve the quality of their data other than ignoring anomalous results. Repeat, repeat, repeat. So take more readings. And you could get other people to carry out the experiment. Describe how the students could develop their investigation to investigate how reaction time changes with another variable. So what else could we look at? So they're still doing the same thing, they're catching the ruler. We've still got the same set of people, but maybe we could use a larger group of students and actually have a look at how their reaction time varies with a variable about themselves, so maybe their age or their height. A car accelerates at a constant rate of 1.83 meters per second squared along a straight flat road. The force acting on the car is 1.80 kN. Calculate the mass of the car. Give your answers to 3 sig fig. So we've got an acceleration here. We've got a force, and we're looking for mass. So you need this formula triangle, FMA. So let's write out the formula we're using. So we're looking for mass, so we cover the M in this triangle and we see that M is F divided by A, so force divided by acceleration. The force we've been told is 1.87 kN, and I'm going to multiply that by 1,000 to turn it into just newtons because I don't want any issues with units. And then we're going to divide that by the acceleration we've been given, which is 1.83, and then when you do that and you round that number to 3 sig fig, you get a value which is 1,020 kilograms. The car accelerates from rest, so that's from 0 meters per second, for 16 seconds. Calculate the speed of the car after 16 seconds. So we know that the initial speed is 0 meters per second, so that's actually u. We're looking for the final speed, which we know we assign v. We've been given a time value, which is t. There's a mention of acceleration, which is a, and we know acceleration from the question above. So let's make sure we're using the correct formula here, which states that acceleration equals final speed minus initial speed over time. So acceleration is 1.83. Our final speed is what we're after, which is v. Our initial speed, well, we were told it went from rest, so obviously it didn't have any speed then, so that's 0, over time, which is 16. So that is the initial part. Oh, someone at the door. Let's sort out this equation a little bit. So we're going to do 16 times 1.83 to get 29.28 equals v minus 0. Obviously, if you minus 0, it disappears. So actually, our final speed is 29.28, which rounds to 29.36 C, the car starts on another journey. Figure 6 shows the graph of the car's movement. So we have a velocity time graph here. Show the distance travelled when the car is moving at constant speed is greater than the distance travelled when the car is slowing down. A lot to do here. So distance on a velocity time graph is given by the area under the curve. And then we need to look for the distance travelled at constant speed, and that's when the velocity is unchanging. So hopefully you recognise that's the flat portion. So really we're looking between A and B, which is why I'm marking out these dotted lines, because I'm looking for this area, which I'm going to call area A. And we need to compare it to the distance travelled when the car is slowing down. So obviously that's when the speed or the velocity drops, and that will therefore be between C and D. So I'm looking down here. So we're looking for this area, area B, which is a triangle, which makes it quite hard. So let's do area A first of all, which is nice and straightforward. It's just a block. So we're going to look at this value, which is 16, multiply it by this x value, which is 15. And once you've done that, you get a value which is 240 meters. So the car travelled 240 meters at constant speed. Let's now look at area B. So if we look along the x-axis, we can see we have 9. Looking along the y-axis, we reach 30. And because it's a triangle, we have to multiply by a half. And then once you've done that, you get 135 meters, which is good because we expected the car to have travelled further at constant speed compared with when it was slowing down. So just right here, area A is greater than area B. So 240 meters is bigger than 135. So that was quite a lot of work for that question. 6. Figure 7 shows the nuclei of 4 atoms. Which 2 nuclei have the same number of neutrons? And so really we need to work out the neutron numbers here. Don't forget that this is the mass number, which is made up of protons plus neutrons. Dog is barking again. And then you've got the bottom number, which is the proton number or atomic number. So basically, if you work out the difference between these two numbers, it will tell you the neutron number. So let's do it for uranium-234. 234 minus 92 is 142. 235 minus 92 is 143. 238 minus 94 is 144. 238 minus 95 is 143. So which two are the same? Obviously this one, uranium-235, and americium-238. So make sure you actually pull out the right option here. That is option B. State what is meant by the term half-life. Well, that's time taken. So these are other definitions you must learn for. Hate it when the pen does that. Half the radioactive nuclei to decay. Part 2. Plutonium-238 is used in spacecraft to provide heat to power generators. One of these generators contains 925 grams of plutonium-238 when it is manufactured. 1 gram of plutonium-238 has a power density of 0.54 W per G. Plutonium-238 has a half-life of 87.7 years. Calculate the average energy released per second by the generator after 263 years. Okay, there's quite a lot going on here. Let's do some highlighting. So we need to work out effectively how many half-lives have taken place in 263 years based on the fact that it has a half-life of 87.7 years. And if you have a look at the question, you can see that the generator starts with 925 grams of plutonium. So basically you need to work out how much of that will be remaining after the set number of half-lives that you've calculated. So let's first of all start by working out the number of half-lives. So we know that 263 years has elapsed. Each half-life takes 87.7 years, so the number of half-lives that will have occurred is 3. Work out the amount or the mass of plutonium left over by doing 3 half-lives on it. So you need to halve it 3 times to get to 115.6. And then lastly, to work out the average energy released per second, take that 115.6 and multiply it by the power density. And you get a value which is 62.4 joules. C. The nucleus of americium-238 can absorb an electron. When this happens, one of the protons in the nucleus becomes a neutron, as shown in figure 8. Describe how absorbing an electron affects the proton number and the nucleon number of a nucleus. This is the crucial bit here. One of the protons becomes a neutron. So clearly, in terms of what happens to the proton number, we've lost 1, so it decreases by 1. And notice that the nucleon number is everything you find inside the nucleus of an atom, so it's made up of both the proton and neutron number. So although you've lost a proton, you've gained a neutron, so actually it will stay the same, the nucleon number. And we're going to write that in the answer box. Deduce which nucleus is formed when americium-238 absorbs an electron. Now, the 238 is obviously the mass number, so the nucleon number. And so, as we've said in the previous question, it will stay the same, so we need 238. However, is it plutonium or is it americium? Well, because the proton number has changed, obviously the proton number is the same as the atomic number and dictates which element you have. So we have a new element, which is why the answer here is plutonium-238. 7. A student investigates how the average speed of the trolley varies with starting height. Figure 9 shows the trolley and runway. Describe how the student can determine the average speed of the trolley. Let's first of all work out what measurements we need in order to calculate the speed of the trolley. That's given by this formula triangle, which states that speed is distance over time. So clearly we need to measure both the distance and the time. So measure the distance along the runway and make sure you say how you're going to do this. So using a meter ruler. Then looking at our formula triangle, we need to measure the time taken by the trolley to travel along the runway. And we're going to use a stop clock to do that. Why have I written runaway? Let's just quickly write use speed equals distance over time to calculate the speed. And what you should always write in these questions is repeat and calculate an average. I can't tell you that enough, that's always a mark. Figure 10 shows his results. Figure 11 shows the student's graph. The trolley has a mass of 650 grams. Calculate the kinetic energy of the trolley, which had a starting height of 0.07 meters. Now, this is obviously the equation we'll need to use, Ke equals half of mass times speed squared. Let's identify what we have. Well, we have a mass. It needs to be in kilograms, so divide that number by 1,000 to do that. Make sure your units are always right. We've got a distance, but we don't have a speed, so we don't have enough numbers, basically, to pop into this equation. So how might we find what we're missing, really, which is speed? Look back up. And this will help you because you've got a graph showing speed against height or speed against distance. Now we need to find the speed at 0.075 meters. So you read up this line here, read across to get your speed, which is 0.6. So now I can start popping in numbers to this equation. And when you've popped that into your calculator, you'll get a value which is 0.117. And obviously it's in joules because it's energy. Determine the gradient of the graph when the height is 0.1 meters. Now notice it's a curve, so we're going to have to find the tangent to this curve. So 0.1 is here, so we need to find a tangent to this line. So you basically draw a straight line, which I'm going to struggle to do because I don't have a ruler that I can use on the iPad. Let's say it's here. Now obviously the gradient is found by doing the change in y over change in x. So the change in y is approximately 0.2, the change in x is 0.05. When you pop that into your calculator, you get a value which is 4. Now it's slightly too high. According to the mark scheme, the answer should lie between 3.5 and 3.6. But I think it's fine because I couldn't draw using a ruler, so I couldn't really draw my tangent properly. But that's actually how you do it. Anyway, I'm going to copy my working down here. Describe how the speed of the trolley varies with the changes in height made by the student between 0.04 meters and 0.12 meters. So we're looking at this portion of the graph between these 2 points. So just because you're describing, you need to say what you see. So as you look at the graph, you can see that for each change in height, as the height increases, the speed of trolley increases. And then you need to look for the steepest gradient to make the comment that the greatest change in speed occurs between 0.04 and 0.9 meters height. A student wants to change his experiment to investigate how different surfaces of the runway affect the speed of the trolley down the slope. Devise an experiment that would allow him to investigate the effect of different surfaces on the average speed of the trolley. So it's worth 3 marks. I'm still going to use my variable format just because that's how I like to lay out investigations. So independent is what you're changing. So the independent variable, change the surface type. So we're altering the surface, the trolley is rolling along, and you want to use at least 3. Then your dependent variable is what you're measuring. So measure the time taken by the trolley. Substitute value into, because after all, after speed, control variables include the trolley itself, so it's mass, and the distance obviously travelled by the trolley, and lastly, angle of slope. And then, as I said previous in this question, repeat, and calculate an average. Make sure you have that phrase set in your mind. 8a. All objects emit electromagnetic radiation. The intensity and wavelength of the emitted radiation vary with the temperature of the object. Figure 12 shows this variation for a filament lamp at 2 different temperatures. The visible region of the electromagnetic spectrum is also shown. And we're being asked in part 1, explain why a filament lamp appears brighter and less red as its temperature increases. So first of all, state what you can see from the graph. So you can see that as the temperature increases, the intensity of the light increases. And that's something you can literally just pull off the graph. And at low temperatures, the intensity of radiation emitted is low, whereas the emitted wavelengths of radiation are high, so that means that the lamp appears dull red. If you have a look at the higher temperature, the intensity of the radiation is much greater, whereas the range of emitted wavelengths is lower, explaining why the lamp appears to be both brighter and less red. So let's make a note of that now. Let's now make a comparison between the high and low temperatures. Intensity of gamma radiation can be measured using a Geiger-Müller tube and counter. The count rate recorded by the counter tube depends on how far away the Geiger-Müller tube is from the gamma radiation source. The equation relating count rate to distance from the source is count rate equals k divided by d squared, where d is the distance from the source and k is a constant. The Geiger-Müller tube is placed 0.7 meters from a source of gamma radiation. So let's just make a note that we have a distance here. The counter displays a count rate of 85,000 counts per minute, so that's our count rate. Calculate the count rate recorded when the Geiger-Müller tube is placed 1.3 meters away from the same gamma radiation source. So we're being asked to find the count rate. We've got a second distance here, but I hope you can see that we can't work out the count rate based on just that distance value because we need the value for k. And luckily we've been given enough information up here to help us find out k. So let's just write out that equation again. So the count rate up here is 85,000. We don't know k because that's what we're after, but the distance was 0.7. Remember, you need to square that. And then in order to work out k, you need to multiply 85,000 by 0.7 squared. And when you pop that into your calculator, you get a value for k, which is 41,650. So k is a constant, it doesn't change, it doesn't matter what distance anything is, that will remain the same. So now we can use that equation again to work out what we're actually being asked, which is the count rate. And I always keep writing these things out just to keep it all lined up nicely. So we're after the count rate, which I'll call x. K we've just found out is 41,650, and our distance is 1.3 squared. So pop that into your calculator and you'll get x, or the count rate, as being 24,645. B. Sulfates and black soot are particles formed by industrial processes. Some of these particles are found in the atmosphere over the Arctic Ocean. The sulfates stay in the atmosphere and reflect, scatter sunlight. The black soot falls onto the Arctic ice. Discuss how a reduction in these industrial processes is likely to affect the temperature of the atmosphere. So in this question, first of all, we need to talk about how black soot and the sulfates would actually affect the temperature of the Earth's atmosphere, and then link it back to how reducing the release of sulfates and black soot, the knock-on effect that would have on the Earth's atmosphere. So make sure you answer both parts here. So let's start by making a statement about the black soot. So clearly the black soot is going to make the ice black. So let's make that point now. And because we've got to link this to temperature, hopefully you know that they're getting at infrared radiation here, because remember, black matte surfaces are good absorbers and emitters of infrared radiation, so it heats up, whereas shiny white surfaces are poor emitters and poor absorbers, but excellent reflectors. So keep these in mind when we're making these points. So the black soot makes the ice black. Black ice is a good absorber of infrared radiation, and therefore the Earth's atmosphere heats up. A reduction in soot production would therefore reduce how much the Earth heats up. So we're answering the question here. For completeness sake, we now need to look at the sulfates. It says that the sulfates stay in the atmosphere and reflect the sunlight, and therefore by reflecting that infrared radiation, it means that less infrared radiation will reach the Earth, and so the atmosphere will be cooler. So we need to make that point before we then answer the bit about how its reduction would alter the Earth's atmosphere. So sulfates reflect infrared radiation, meaning that less reaches the Earth. And so the Earth's atmosphere remains cooler. But decreasing the amount of sulfates would therefore mean that less infrared radiation was scattered and more reached the Earth. So actually the black soot and the sulfates, I hope you can see, have opposite effects. Explain what happens to the wavelength of light when it passes from air into glass. So notice this question, we're being asked about the wavelength of light. Now, when a light ray enters a denser medium such as glass, hopefully you know it slows down, which means its velocity decreases. Now, we're being asked about the wavelength, and hopefully you know that there's an equation linking wave speed, frequency and wavelength. So hopefully you can see that if that wave speed decreases, if we look at a rearrangement of the equation, if you decrease the value of v while maintaining the same frequency, hopefully you can see therefore that this proves that the wavelength of light decreases. So you want to make a point, which is that first of all state what happens to the wavelength. So the wavelength decreases because upon entering the glass, the wave speed decreases whilst the frequency remains the same. And then write the equation which proves this, which is wave speed equals frequency times wavelength. B. Figure 13 shows a beam of red light approaching one side of a rectangle glass block. The beam of light will pass through the block and leave through the opposite side. Discuss the path of the wavefront AB as it enters and leaves the block. So here's the wavefront here, just so that you're aware. So hopefully you can see that the A part of that wavefront will reach the glass block before the B block. So let's make that statement first of all. The real reason for this is it's worth 6 marks, so we're really going to be scraping the barrel here to try and say as many different things as possible. And then what happens? Well, remember we have a normal line at 90 degrees, and this wave will be refracted towards the normal. Try and keep them parallel. That's not very parallel. Let's write the wave slows down upon hitting the glass block and is refracted, try and include some nice scientific words here, towards the normal. As AB reaches the interface, so the separation between the glass block and the air, so here there'll be another normal and the wave will bend away from the normal. Try and keep them parallel. So this last point, notice that the refracted ray is parallel to the incident ray. The incident ray is the one which actually enters, so down here. So yeah, quite a lot to say here. Having a look at the mark scheme, they're quite obsessed about the difference between A and B. So there's another mark for saying that by the time B reaches the block, it will have travelled further than A. And then at the other face, you can say that A exits first. But I don't know, I prefer my answer. C. The distance between Earth and the Sun is 1.5 times 10 to the 11 metres. And that's obviously a distance. Look at how I always like to label so I know what I've been given. Light takes 500 seconds to travel from the Sun to the Earth. So we've got a time. The wavelength of red light is 670 nanometers. So that's wavelength. Calculate the frequency of the red light using only the data provided. So that's F. So at this point, we are trying to work out what equation we could use to actually find out the frequency. So let's first of all look at this equation, which states that wave speed equals frequency times wavelength. However, we can't use that equation immediately because we don't have enough information. Although we're being asked to find frequency, We've been given the wavelength. We don't know the wave's speed or velocity. So that's where distance time comes in. Hopefully you know that distance equals speed times time. And so therefore we're going to use what we've been given, which is the distance here, that will go in here, the time, that will go in there, so that will enable us to work out v, and then we can substitute that v into this equation to help us find out f. So let's get going by first of all stating that v, so the speed of the wave, is distance divided by time. Our distance is 1.5 times 10 to the 11 meters. Our time is 500 seconds. And when you pop that into your calculator, you get this value, 3 followed by 8 zeros. So that's 300 million meters per second. Now we're ready to calculate frequency. So frequency equals, we're rearranging this equation, velocity over wavelength. Velocity we've just calculated as being 300 million meters per second. Our wavelength is 670 nanometers. Be careful here. We've got to convert nanometers to meters, and the way we do that is by doing times 10 to the minus 9. You must know this. And when you pop that into your calculator, you get a value which is 4.48 times 10 to the 14 hertz. Great, we're on to the final question, question 10. In a nuclear reactor, a chain reaction is produced and controlled. Uranium-235 is the isotope used in many nuclear reactors. Explain how the fission of uranium-235 can lead to a chain reaction. So really you need to say what fission is. So hopefully you realise that it's a neutron being fired at the uranium nuclei. And remember that that uranium nuclei splits to form daughter nuclei plus 2 to 3 neutrons. And so really what we have to do here is state this. So fission is the splitting of the uranium nuclei. Two to 3 neutrons are released, and remember these go off and collide with other uranium nuclei. Causing further fission. And remember, this is a very dangerous process because it sets up a chain reaction, which if allowed to get out of control could cause a huge explosion. Nuclei of beryllium-9 do not absorb neutrons. Instead, nuclei of beryllium-9 absorb alpha particles and emit neutrons. Give a reason why a chain reaction can result from the emission of neutrons by uranium nuclei, but not by beryllium nuclei. Well, this is all to do with the fact that when you're doing nuclear fission and you're setting up a chain reaction, you've got to have the same particle colliding with the nucleus as the one that is produced when the nuclei splits in half. And we've been told that this is alpha particles and that it doesn't absorb neutrons. Explain what happens inside a nuclear reactor if neutron speeds are not controlled. The crucial thing to notice here is the fact that neutron speeds should be controlled in order for a nuclear fission reaction to take place. Bizarrely, the slower they travel, the more likely they are to collide with the uranium nuclei. So the question asks, explain what happens inside a nuclear reactor if neutron speeds are not controlled, i.e. what happens if the neutrons are travelling really fast. And actually what happens is that there are fewer reactions within the nuclear reactor. This is because, and we're explaining it here, the neutrons are not slowed enough and are unable to split the uranium nuclei. Describe how the energy released in the chain reaction in a nuclear reactor is used to drive a turbine in a nuclear power station. So what is the whole point of carrying out these nuclear fission reactions? Well, clearly we're trying to generate electricity, and we do that through the use of a turbine which turns a generator. But let's go back a step and look at how that chain reaction leads to the turbine being driven. So that's all to do with the fact that the reactor is surrounded by water, which we call the coolant. The thermal energy released from the chain reaction heats that water, turns it into steam, and it's that steam which actually drives the turbine. And we are done. I really hope you found this video helpful, guys. I'm really making an effort to do as much Edexcel 9-to-1 as possible, so do